example 14 piggybacks off of example 13. Just so you know, example 14 was not included in example 5. I added this one because it is related to example 13. Really quickly, let's go back and glance at example 13 so you remember what went on there. We were buying a new car, and instead of taking out a car loan, we decided to save up for the car through a savings account. So what we had to calculate was the amount of money that we needed to deposit every month in our savings account. And the savings account earn 4.5% interest compounded monthly. And we wanted to save up and make these monthly contributions over a 3-year period. And we wanted to accumulate $18,000 to purchase our car. So we did the calculation and we figured out that we needed to put away $467.94 into our savings account every month in order to save up the $18,000 for the car in a 3-year time period. Okay, so now let's read example 14 because it's very similar. Okay, so suppose you could only save $200 each month instead of the $467.94 that we calculated in example 13. How long will it take to accumulate the $18,000 for the new car by depositing $200 at the end of each month in a savings account earning 4.5% interest compounded monthly? Okay, so you are still saving for the car. You're still saving the same amount, $18,000. You still have the same interest rate of 4.5%. Okay, you're still making monthly contributions to the account. Your interest is compounded monthly, so those parameters have remained the same. Okay, so what has changed is maybe $467.94 is a stretch. Okay, maybe because of your job and your other financial obligations, you can only afford to save $200 every month. Okay, how long is it going to take to save up $18,000 for this new car? Okay, well, we have an idea of what our answer is going to look like. Okay, again, when you look at this question, the question is how long will it take? Okay, so you're solving for time. Okay, back when we said it was going to take us 3 years to save the $18,000, we said that we needed to save $467.94 per month. Okay, now we can only afford $200 a month. Okay, so since we're saving less each month, that means it's going to take us longer than 3 years to save for this $18,000. Okay, so make sure once you solve this problem, you get an answer that's bigger than 3 years. Otherwise, it's not going to make sense. Okay, so you are saving money. You're saving $200 each month. Okay, you're saving money. It's regular deposits. Makes it an annuity. Okay, so you're going to use your future value of an annuity formula here. So let's go ahead and write that down. And we know, since we read this little phrase, how long will it take? We are looking for the time value. Okay, so we should know everything else. Okay, the interest rate did not change, still 0.045. Okay, the interest is being added to the account monthly, compounded monthly. We're also making monthly deposits, so ILM is 12. Those two things should coincide. Okay, P is the amount of each deposit, $200. And then A is the amount we want to accumulate, or our final account balance, however you want to think about it. That is $18,000. Okay, so let's plug into this. So we're going to get 18,000 is equal to 200 times 1 plus 0.045 divided by 12 raised to the 12t power minus 1 all over R over L. Okay, you've got to solve this for time. Okay, we learned from doing compound interest that solving for time can be a bit of a challenge because the t is trapped in the exponent or the power. Okay, and it was already complicated enough when we were doing compound interest, but the future value of an annuity formula is even more complex than the compound interest formula, okay? It's still going to involve logarithms, okay? Because the formula is a little more complicated than compound interest, it's going to take a couple of additional steps, but in general, you do it the same way. You want to isolate the piece that has the t, or the exponential piece, and then once you have it isolated, you're going to go ahead and take the natural log of both sides. That will bring the exponent down. It'll free the t from the power, and then you do your division of logarithms, and then you round up time always to the nearest whole, or to the next whole number, and then you interpret the time value that you get, okay? All right, so let's look at this. Again, you have another exponential equation. You got an equal sign. Your variable is t. It's trapped in the power or the exponent. Your first step is always isolating the thing that has the t, okay, the exponential piece. This is what we need to isolate, okay? We can detach everything else from the 12t except for what's in parentheses, okay? So our first goal is going to be working towards isolating what's in the pink box, okay? All right, so to do this, we've got to do three things, okay? First thing we're going to do, okay, see how all this stuff is in brackets, okay? The 200 is not in brackets, so it's kind of on its own. So we're going to get rid of it first. We're going to start by dividing both sides by 200. Okay, so if you take your calculator, and I'm not going to show you this because it's going to come out to be a nice number, but if you do 18,000 divided by 200, you're going to get 90 on the left, okay? And then on the right, the 200s will cancel and leave you with, well, let's see. You don't actually need your brackets anymore. The brackets were just there because of the 200 on the outside. Okay, so let me get rid of that. Okay, so it's going to leave us what is inside the bracket. So 1 plus 0.045 divided by 12 to the 12t minus 1 divided by 0.045 divided by 12. Okay, so it's going to leave you with that. Okay, the 200 has been taken care of. Okay, you're still after isolating this guy. Okay, so the next thing you do, okay, the 1 is attached to the thing in the box, okay? All this stuff is in the numerator, okay? So our next step in isolating the thing in the box is getting rid of this, okay? Because it's in the denominator. It's kind of off in its own land, okay? So since you're dividing by this quantity, you're dividing by this r over m value, to undo that, you're going to multiply by it. Okay, since you did that to the right side, you're going to have to do it to the left side. Okay, so this is what you're going to do. So we're going to multiply both sides by this quantity. Okay, so what will happen here, okay, is on the right side, you have 0.045 divided by 12. You have 1 in the top and 1 in the bottom, so they are going to cancel. Okay, and that is going to leave you with 1 plus 0.045 divided by 12 to the 12t minus 1 on the right. Okay, on the left side, okay, we can go ahead and figure out what that is. Okay, so let's go ahead and figure out what that is. So let's go to the calculator. Okay, we've got 90. We're going to take that and multiply it by 0.045 divided by 12. Okay, and actually we get something nice, so we can go ahead and write that down. The left side is going to be 0.3375. Okay, so like this, 0.3375. Okay, all right, so that brings us here. Okay, we are still trying to isolate this guy because it contains the t. Okay, all right, so this is kind of on its own, okay? So the opposite of subtracting 1 is adding 1. So we're going to go ahead and add 1 to both sides, okay? That is going to give us 1.3375 is equal to 1 plus 0.045 divided by 12 raised to the 12t power. Okay, and now this quantity in parentheses that's raised to the 12t power is isolated. Okay, remember the 12t is attached to the parentheses. You cannot separate these guys as it's written. Okay, they are married to each other. Okay, so now that you've got this exponential piece, the quantity that's being raised to the 12t power, you've got that isolated. You want to get the t out of the exponent. That's why this is so difficult to solve for, because the t is in the exponent. So that's when you go ahead, once you've got that exponential piece isolated, that's when you go ahead and take the natural log of both sides. Okay, so on the left side, we're going to get the natural log of 1.3375 is equal to the natural log of 1 plus 0.045 divided by 12 raised to the 12t power. Okay, and you have to take the logarithm, because if you have the logarithm of something to a power, then you're allowed to bring down the power and free the t from the exponent. Okay, if you do not take the logarithm, you cannot bring the 12t down. Okay, all right, so let's see, I'm running out of room here. So I may actually continue this on a separate sheet of paper because I am running out of room. Okay, so, and I will attach it in my notes when I scan this for you. Okay, so let's see here. Let's continue. This is example 14. Okay, so what's going to happen, this is going to give me natural log of 1.3375 is equal to 12t times the natural log of 1 plus 0.045 divided by 12. Okay, and again, you don't write the exponent because now it lives here. Okay, so once you have that, okay, think about it. You're going to put this in the calculator. Okay, it is going to be some ugly decimal. Okay, so it's going to be just a number. Okay, then this logarithm you're going to put in the calculator. It is going to be some ugly decimal. Okay, your goal is to solve for m times t. So you want to solve for this guy. Okay, not just the t, the 12t. Okay, just like you did with the compound interest formula when you were solving for time. You always solve for m times t. Okay, so since we're multiplying 12t by this logarithm, we need to divide this logarithm off in order to get 12t isolated. Okay, so we're going to divide both sides by this logarithm. Okay, whatever you do to one side, you have to do to the other. Okay, so it's going to look like this. Okay, and I'll go ahead and rewrite it for clarity. Okay, 12t is going to be this logarithm divided by this logarithm. The order in which you divide the logarithms matters. So make sure you understand why this logarithm is in the numerator and this one's in the denominator. It matters. Okay. All right, so we can go ahead and punch this into the calculator and that will give us a decimal for 12t. Okay, so we're going to get natural log of 1.3375 close parentheses divided by natural log of 1 plus 0.045 divided by 12. Okay, here's your decimal. Okay, so let me go ahead and write that down. Okay, so 12t is going to be equal to 77.69256367. Okay, just like you did with compound interest when you were solving for time, you need to take this decimal and round up. Okay, so we're going to get 12t is equal to 78. Okay, you always round up, even if it had been 77.29. Okay, all right, so now we stop and interpret our answer. Okay, so there's a 12 in front of the t, so that means we are talking about 78 months. Okay, that's how long it's going to take us to save the $18,000 for the car. Okay, so 78 months is the answer if we can only save $200 a month. Okay, again, it did not specify in the question how you need to express the answer. It just asked how long is it going to take. Okay, so again, if you were asked in my math lab or on a quiz or a test to express the answer in the total number of months, the answer is 78 and you're done. Or if you're expected to express it in years in leftover months, you need to know how to convert to that, okay? So we'll go ahead and do the conversion to that really quickly. So remember how you do this. We know it's going to take a total of 78 months, okay? So we're going to go and we're going to say take the 78 months and we're going to divide by 12 because there's 12 months in a year, okay? So if you do 78 divided by 12, okay, you're going to get 6.5 exactly, okay? So that's actually years here, okay? So it's going to take you 6.5 years, okay? So remember, half of a year is 6 months, okay? So it should be 6 years, 6 months. That's another way to write the answer, okay? If you didn't know how to interpret the 0.5 as half a year or 6 months, okay, you could have taken the 78 and divided by 12 and gotten the 6.5 and said, hey, that's 6 whole years, and then I've got to figure out how many months are left over. So then you would go, okay, 6 years, there's 12 months in a year, that's 72 months total. So 72 months in 6 years. And then subtract out. I've got 78 total months, subtract out the 72, and that's going to give me 6 months left over. Okay, so these are all equivalent ways of expressing the answer. It could take a total of 78 months, which is equivalent to 6.5 years, which is 6 years, 6 months. Okay, does this answer make sense? Absolutely, because in example 14, we can only save $200 a month. And so it's going to take us longer to save the $18,000 than it did in example 13. Remember, in example 13, it was going to take you 3 years to accumulate the $18,000, but you were able to save $467.94 a month. So that totally makes sense. Okay, so